Greetings students, this is the lecture for dynamics. I will do a quick, perhaps not so quick video on how to solve the assessment problem in the assessment 1B. So the details in writing is there for you to read in your own time. And remember the instructions were to work out your answers to 3 decimal places in millimeters and megapascals, and you would be marked correct if you got within 0.01 millimeters or 0.01 megapascals. That was the criteria. It was clearly specified. So very briefly, the problem is that there is an isosceles triangle stacked on top of a rectangle. The two taken together act as a composite beam. It is also specified the various geometry parameters and the material properties. And essentially the question specifies that you must work out the distance from the neutral axis to the centroid, distance from the neutral axis to the centroid, the stress at the centroid, the stress at the centroid, and the stress on the neutral axis. The bending stress at the intersection of the neutral axis, which is the z-axis, and the plane of symmetry, which is the y-axis, is automatically 0 because it is always on the neutral axis. The definition of a neutral axis is that all the stresses on the neutral axis are by definition 0. So immediately sigma O is 0. This is 10 points. You would specify 0.000 megapascals. You get 10 points and you get 20% in the test. There was no calculations required for question E. It was just to test whether you understood the concept of a neutral axis. In any case, let's go ahead and try and solve the problem. Okay, how do we solve the problem? Well, we've got the neutral axis, we've got the centroids, and we are given the height of the triangle is h, the height of the rectangle is t, and the breadth of both the base of the triangle and the rectangle is b. These are random values in red. Different students would have different values in their particular assessment. What we do is we express all of these heights in terms of a single variable, and I've chosen h2 as the variable. So just looking at the geometry, I can express h1, h3, h4, and h5 in terms of the other heights, the height h, t, and b, noting that the centroid is 1/3 of the height from the base of the triangle, and the centroid of the rectangle is in the middle, half of the thickness, half of the breadth. So we know that. So what we do is just from the geometry, we can work out these parameters. Okay, so let's go ahead and work out the information. So purely from the geometry, what we have is the following. We immediately have that h1 minus h3 is 1/3 of the height. Therefore, h1 is equal to h3 plus 1/3 of the height, and we have h2 minus h4 is equal to 1/2 t. Therefore, h2 is equal to h4 plus 1/2 of t, and we have h3 minus h2 is equal to 1/2 of t. Therefore, h3 is equal to h2 plus 1/2 t, and therefore that would then mean h1 is equal to h2 plus 1/2 t plus 1/3 h. Okay, where is these expressions coming from? h1 minus h3, h1, the distance from here to there, that distance minus that is just 1/3 h. h2 minus h4, this is below the axis, it's a negative, that's a negative. Negative minus a negative is positive, so this distance between h2 and h4 is 1/2 t. And h3 minus h2, h3, which is positive, minus a minus, this distance over here is just 1/2 t, because we know the centroid is in the middle. That's 1/2 t, that's 1/2 t, we know the centroid is 1/3. So we have expressed all of the terms in terms of one unknown, h2. So h1, let's just get this right. This is h1. Yep. Undo that. Okay, that's correct. That's correct, and that is correct. So we know all of the geometry in terms of one unknown, h2. What is the next step? We're going to work out the neutral axis. How do we work out the neutral axis? We have an integral equation to work out the neutral axis. What is the equation that we want to solve? The equation that we want to solve is the following. E1, integral of 1 on the area 1 dA plus E2, integral on the area 2 y dA is equal to that. That's a Young's modulus. That's a Young's modulus. That is a first area moment of inertia. And then, of course, the second area moment of inertia. These are two different things. The first area and the second area moment of inertia are two separate things. This one can use parallel axis theorem. And this one cannot use the parallel axis. Okay, so how do we actually work that out? Okay, so in your textbook, this is the concept. I'm just going to quickly revise it. There is some arbitrary region and there is a centroid. Typically, there is a coordinate system, x and y. We have a distance from the centroid to the x-axis, which is y bar, and we have a distance from the centroid to the y-axis, and that is called an x bar. And we have these formulas. X bar is qy over a, and that is equal to x dA over dA, and we have y bar is equal to qx over a, which is equal to the integral of y dA over the integral dA. Have a look at this. The integral of y dA, what that means is in this particular case, the y-axis is vertically upwards, the x-axis is the horizontal, and the integral of y dA is the area of all of this times yes, that's correct. The integral of y dA is area times y bar. So what that means is if we have a vertical axis, a horizontal axis, and we want to work out the integral of y dA, we just take the area, find the distance from the centroid to the horizontal axis, and that is the first area moment of inertia. Okay, so for our particular problem, what do we have? For our particular problem, we have a triangle sitting on top of a rectangle. We have a y-axis. We've got a centroid. We have a centroid. And we have a z-axis. We are given the height as t. We are given the breadth. This is our region 1, and this is our region 2. We know the height h1 and h2 in terms of h2, and then we want to find out then that would just be the area of the triangle. The area of the triangle is half base times height multiplied by the distance from the centroid to the neutral axis, which is multiplied by h1, and similarly we would have the area multiplied by h2. We know H1, we remember it to be H2 plus a half T plus 1/3. Okay, substitute it, and then this would imply E1 times the area multiplied by H2 plus a half T plus 1/3 height close plus E2 times the area, which is BT, into H2. All of that is equal to 0. We can solve that for H2, and then this would imply H2 is equal to, after a lot of simplifications, you can solve this equation, do various simplifications, and right at the end of the day, you'll end up with the following formula. And then H1 would be H2, which is all of that stuff. Okay. Let's see if that's making sense. Where are we and what are we doing? We had the structure, we used the geometry, we expressed all of the geometry in terms of one unknown, H2. So H1, H3, H4, H5, everything in terms of H2. We applied the integral equation, we worked out the first area moment of inertias as the product of the area and the distance from the centroid to the neutral axis. We substituted that into the integral equation, we solved the equation for H2, and then we substituted for the formula for H1, and then we got an answer. And then that's where we pause. Next, we want to work out the bending stresses. How do we work out the bending stresses? Okay, let's do it like this. Okay, let's remember the definition of a bending stress. Okay, what is the bending stress? When there is an applied moment. Okay, let's see if we understand what that means. We have a region 1, the triangle. We have a region 2. For any y value within the green triangle, y value, the distance from the neutral axis to some point in the green, that will give us the stress for any point within the triangle, the green, including the centroid C1. For the yellow, the rectangle, any distance y, either positive in this region over here or negative in that region, will give us the bending stress in the rectangle, including the centroid. What is the distance from the neutral axis to C1? Well, that's just h1. The distance from the neutral axis to C2, that's just h2. But we know the formulas for h1 and h2, which we worked out. Therefore, we can just as well put it into the bending stress formula. Therefore, that would then just be sigma 1 Okay. Now, well, we've got the bending moment, the Young's modulus, the h1, the h2. We just need to work out the moment of inertias. What are the moment of inertias? We have a triangle, we have a rectangle. And these are what is known as the second area moment of inertias. Integral of y squared dA. Now, we don't need to work this out from first principles because these formulas are standard formulas that we are expected to remember or be familiar with. So we know, referring to the back of our textbook for the sake of argument, we would have I1, which is a triangle. The formula for the second area moment of inertia is the breadth times the height cubed over 36, but that is at the centroid. We can apply the parallel axis theorem, and then we add the area times the distance squared, and the area of a triangle is a half base times height multiplied by the distance squared, and the distance squared will be h1 squared. And then for the rectangle, we all remember the standard formula 112 breadth height cubed, 112 breadth height cubed plus area times the distance from the centroid to the neutral axis squared. And then we have the distance from the neutral axis to the centroid, h1. We have the distance from the neutral axis to the centroid, h2. We have sigma 1, the stress at the centroid, and we have sigma 2, the stress at the centroid, and we know the stress at the neutral axis is 0. And that is the problem which is solved. And that is the entire solution right there. Okay. So we had the problem, we did the schematic, we determined the geometry in terms of all the distances. We expressed these distances in terms of one unknown. We put it in the integral equation. We worked out the area first moment of inertias. We substituted it into the formula. We solved the integral equation for H2. We deduced H1 in terms of H2. We substituted the H1 and H2 value for the bending stresses, and we deduced a formula for the area second moment of inertia. And this is all the symbolic equations at the end of the day. So that is the problem, which is basically solved. And then if we look at it, that is how we would solve the problem. It is one page of calculations. We substitute the information, and then we can take it from there. All right, I think we will pause over there. In the next video, I might show you how to use a computer program. But for now, I think that is it.